Right, hey everybody, this is going to be the tutorial video for section 11.3 on the surface area of pyramids and cones. So I'm going to start by presenting my screen. And you should have the 11.3 notes up and ready to go. Okay, so today's big topic is all about pyramids and cones. So moving on in the wonderful land of 3D. Give me one sec. I'm going to hide my camera, but I'll keep my microphone on. That way at least you can focus on the notes. Okay. All right, so goals of this section, we're going to be talking about pyramids and cones, and so far in this chapter we've been focused on the wonderful topic of surface area. So we're going to be finding the surface area of a pyramid and the surface area of a cone. You probably have some ideas for what these shapes look like. When you think of pyramids, you probably think of the Great Pyramid of Egypt. When you think of cones, I always think of a party hat or a traffic cone. So our mind has ideas about what these shapes are, but they are different than the prisms and the cylinders that we talked about the other day. So think about how we found the surface area of a prism or a cylinder. I just draw like a rectangular prism or like a triangular prism. One thing that I notice is there's two bases. Here, there's two bases here. And even with a cylinder, remember, a cylinder is not a prism because the circles at the top and the bottom are not polygons. However, all of these things have the common characteristic that they have two bases. So when I compute the surface area, it's going to be the lateral area plus 2 times the base area, since each of those shapes has two bases. Remember, the lateral faces for these prisms are going to be all the rectangles surrounding it, not including the bases. Same for the triangular prism. For the cylinder, the lateral area is that soup label that, if you were to think of this as a soup can, it's going to be the area of that label that surrounds the can, not including the circle on the top and bottom. But the big thing to notice here is it's two bases. And whenever we deal with a pyramid, and we'll see also a cone, there's only one base. And that's one big difference. When I look at a pyramid, it's still a polyhedron, but it only has one base. And instead of all of the lateral faces being rectangles like they are in the case of the prism, now you'll notice that all of the faces that are not bases, that rhymes, are triangles. They are no longer rectangles. So all of the lateral faces for a pyramid are going to be triangles. They are no longer going to be rectangles. And the reason for that is they meet up at this point at the top instead of meeting up at another base. And that point at the top is what we call the vertex of the pyramid. We're mainly going to be looking at what are called regular pyramids, which just means that the base on the bottom is going to be a regular polygon, equilateral and equiangular, which makes for an easier problem. So that's good. Some different pieces to notice. I'll fill in this blank in a minute. If I was to look at one of my pyramids, so I'll just look at this one on the left. Here's the vertex I just mentioned at the top. That's the point where all of these lateral faces meet up. By lateral faces, I'm talking about all of these triangles that you see surrounding the pyramid that lead up to the top. And in the case of the one with the hexagon on the bottom, there's 6 of those triangles. This one has a square on the bottom, so there's only going to be 4 triangles that lead up to the top. Those are the lateral faces. Again, that means they don't include the base. The lateral edge, I'll do these in red. This is just the side lengths of the triangle, not including the one side on the bottom. So there's going to be 6 of them in this problem. And they're all congruent. That's one nice property. All of these lateral edges have the same length. The base edge is just going to be all of the side lengths, all of those edges that make up the base on the bottom. So I'll put those in blue. Those are my base edges. And the altitude is the distance from the vertex, cuts through the pyramid, and goes down to the center of the polygon base on the bottom. So that segment that I labeled in purple here, usually we use the letter H. And the reason for that is the altitude is the height of the pyramid. This forms a right angle with the base. Okay. So that takes care of the different pieces of the pyramid there. Okay. This one would be called a hexagonal pyramid. We always name it by the shape of its base. So since it's a hexagon, I call it hexagonal. The one that I have on the right over here is what I would call a square pyramid, since the base on the bottom forms a square. A nice regular quadrilateral. This is a square pyramid. And you'll notice that most of the pieces I have labeled are the same, but I introduce one new one. Here's my altitude in red. Goes from the vertex, forms a right angle with the base. This distance from the center to this midpoint of this base edge, okay, that's just the apothem of my square. I'm going to label that A for apothem. And this new piece right here that I have labeled, I'm going to put it in green. This height of one of the lateral faces, if you look at it from a side view, here's my base edge, or not my base edges, these are my lateral edges. We'll call this E. E and E for lateral edge. If I look at the height of that triangle, that is actually what we call the slant height of the pyramid. Because if you look at it from the pyramid's point of view, it's on a slant. That green segment that I drew is tilted. Okay? So the slant height is just the height of each lateral face. It's the height of one of those triangles that leads up to the top of the pyramid. And you'll notice we make a nice little triangle that almost stands up on top of that square on the bottom. That triangle is going to be really popular to use in problems. It's a triangle that stands up on the base. And I could have drawn in a lateral edge for this hexagonal one also. Here's a lateral example of a lateral edge. This segment I just drew in blue would be a lateral edge. And it always will split that base edge in half. So that's just some vocab to get you started. How do we actually find the lateral area and the surface area of a pyramid? Let me just erase. Well, let's take the case of the square pyramid. There's 4 triangles surrounding it, and they all lead up to the top at the vertex. Each of those triangles has a height of L. L is the letter that we use for the slant height. I should have mentioned that before. We use a little cursive letter L for the slant height. So the height of each of these triangles is L. What I'm going to do is just make a little rectangle surrounding all 4 of these triangles. Lateral area does not include the base on the bottom, so I'm only trying to find the area of these purple triangles right now. And what you'll notice is there's some extra triangles that got added into this rectangle also. I got 1 here, 2 here, 3 here, and if you were to put together these 2 on the edges, they would form a 4th one. So you have 8 identical triangles on the inside. All of the lateral faces for these regular pyramids are identical to each other. Okay? So if I want to just know how much area is inside the purple ones, let's figure out how much area is inside the rectangle first. The base of this rectangle, I'm calling each of these base edges S. So if I add them all up, S plus S plus S plus S, well, I'm using the square pyramid that I had from here. S plus S plus S plus S is just the perimeter. So I'm going to call this bottom P for perimeter of the base. And then I'm multiplying it by the height since it's a rectangle. The area of all of this space inside is P times L, base times height. But that covers everything inside here, all of this yellow space. I need to take out half of those triangles that I didn't use. I don't need the ones on the ends that make one triangle. I don't need this one, I don't need this one, and I don't need this one. So I'm going to take all that area that I found and I'm just going to cut it in half since I'm only using half the triangles. That's my lateral area for a pyramid. It's 1/2 the perimeter of the base. Perimeter of base, we saw that notation with prisms the other day. And little cursive L is the slant height of the pyramid. So that's the slant height. And don't forget the 1/2, that's important. This is your formula, and it'll be on your formula sheet that I post also. That's the lateral area of a pyramid. To get the total surface area, well, you're going to need the lateral area, but then you're going to have to add on the base area on the bottom. Notice I'm only using one capital B this time because I don't have two bases like I did in the case of the prism or the cylinder. I'm only using one base. It's only got one bottom this time. So that's how I find my total surface area for a pyramid. All right, let's do some practice. First example wants us to find the surface area of a square pyramid. They're already telling me the shape of the base. And they're telling me that the base edges are all 7.5 feet long, and the slant height is 12 feet long. So I'm going to show you how to draw one of these. It's not too bad. If you want to draw a square pyramid, you start by drawing like a tripod. Draw an L, draw a segment coming out from the little cusp on the bottom. I'm going to draw the vertex of the pyramid at the top. I'm going to label it in red. And what I first want to do is I want to make my square on the bottom, so I'm going to focus on that. It is a little bit tilted. So I'm going to draw one edge coming out here, and I'm going to make that segment just as long as the one I have across from it, so that these two dots line up. And then I'm going to connect fourth side, so I get my square. Take a pause there. Make sure you have that. And now all I'm going to do, add one more purple dot. I'm going to draw segments connecting the red dot at the top to each of the purple dots on the bottom. And I'm going to get a nice pyramid. So there's one lateral edge. There's another lateral edge. And there's another lateral edge. Okay, not a perfect pyramid, but it'll do the trick for the purpose of this problem. What did they give us now? They told us that it's a square base, and each base edge, so I'm going to tick mark these in purple, each of those is 7.5 feet long. And they told me the slant height, I'll do this in red, I'm going to choose to draw it on this right face. That's the height of one of the lateral faces, one of the triangles. So one of these slant heights is 12 feet long. Okay. So just to give you a visual. What do we need? Well, we want the surface area of the entire pyramid. Let's start by getting the lateral area that's going to be part of it. Let me erase these dots. The first thing I need, let's do lateral area. Using my formula from the last page, it's 1/2 the perimeter of the base times the slant height. The base is a nice clean square. And I know how to find the perimeter of a square. I just take the side length and multiply it by 4. So my perimeter of my base is going to be 7.5 times 4, which is 30. So 1/2 times 30. And then the slant height they gave me was 12. 30 divided by 2, 15. 15 times 12 is 180. So I get 180 square feet just from the triangles. If I was to paint all of the sides of the pyramid, that's how much paint I would need to cover everything except the base. But if I wanted to paint the bottom, this answers the question. They want the surface area. It's going to be the lateral area. And remember, it's only one base. Since there's no base at the top, it's a vertex. Well, the base is just a square. So we know how to find the area of a square. We take base times height. The lateral area was 180. And the base is just going to be, well, there's one part of the square. That's the base. There's the height of the square. 7.5 times 7.5. I'm just going to write that as 7.5 squared. If you add that up, this is 180, and 7.5 squared is 56.25. Add those together, and your total surface area is going to be 236.25. And obviously, you have a calculator at home. You can type that in. Okay. So that's the entire surface area, including the base on the bottom. Let's look at another one that has a square base. This one offers something a little bit different. You'll notice in this problem, still a square pyramid. Okay, I see a square on the bottom. They gave me the base edge. Notice in this one, though, they didn't give you the slant height. They actually gave you the height or the altitude of the pyramid, because it goes from the vertex, and instead of being the height of the triangle, it's actually the height of the whole pyramid. So that 6 that they gave me is the height of the pyramid. I want to find the surface area. Well, I know that the slant height is involved in my formula for the surface area. So I'm going to have to find that. First thing I'm going to do is I'm going to draw that triangle that I referenced on the first page right here. This little one. Because I know I can make a nice right triangle out of that. I've already got the height labeled. I'm going to draw the center of the square on the bottom, and I'm going to draw that apothem in that goes to the midpoint of the base edge. What's awesome about a square is the apothem's length is just half the length of the base edge. This whole thing is 4, but I'm only going out to the middle. So if the whole side length of the bottom is 4, that tells me that this base edge, or I'm sorry, this apothem is only 2 units long. It's half of the length of the base edge. The whole altitude was 6. Here's my right angle. I'm going to make my slant height the hypotenuse. I'm going to do that in pink. So it's going to be the height of one of these triangular lateral faces. So that purple piece I just drew is L. Makes a nice right triangle that stands up on top of the bottom. So there's the triangle I'm focused on. Little Pythagorean theorem. Height is 6. That apothem is 2. I need L. I'm just going to do, pen's acting up. Uh-oh, what happened? Undo, undo. There we go. There's 6, so I'm going to do 6 squared plus 2 squared equals L squared. I get 36 plus 4 is 40 equals L squared, square root both sides. If you break down rad 40, rad 4 times rad 10 is going to be 2 rad 10. Oh my goodness, why does it keep doing this? There we go. So I get 2 rad 10 for my slant height. So now I can actually go and compute man, this is having some really bad. I don't know why it's doing that. Okay, sorry about that. Still learning some features of this smartboard. Okay, so let's do the lateral area. The lateral area is going to be 1/2 the perimeter of the base times the slant height. Perimeter of the base, 4 plus 4 plus 4 plus 4 is 16. So 1/2 times 16, and then times, we just found the slant height was 2 rad 10. So I get 8 times 2 would be 16 rad 10. But I'm not done because they actually wanted the total surface area, so that at least gives me the lateral area. Now I'm going to do the total surface area. Well, that means I'm going to need the lateral area plus 1 base's area. There's only 1 base. So 16 rad 10 plus the base area, in this case, capital B, is a square, so just 4 times 4. That's 16. Can't add these together because one of them has a rad 10, but the other one does not. It doesn't really matter because the problem asked me to round to the nearest tenth anyway. So I would just type that into my calculator. So if you type that in, be 16 rad 6, enter. Oh, not 16 rad 6, sorry. 16 rad 10, and then plus 16. You can do it in one line too. I like to do things in separate steps. So 66 point, we're going to round that 5 up to a 6. 66.6 meters is what we're measuring in, so this would be meters squared. Okay. So get a couple examples of a square pyramid. I want to do one that has a hexagon as the base. Works the same way, but it's nice to look at ones that don't have a square base. So we're going to look at one that's a hexagonal pyramid, and we're still going to round to the nearest 10th. Looking at my problem, let's see what they actually gave me in this one. Looks like they gave me one of the base edges is 6, which means I know all of these base edges have to be 6 since it's a regular polygon. So that's helpful. They give me the slant height. I can tell it's the slant height because it's the height of one of those triangular faces. Do this in red. I'm going to label that cursive L for slant height. And they also give me the apothem since it goes from the center to the midpoint of the base edge. So I've got an apothem as well. Okay. So let's see what we need. Let's first we need surface area. So I'm going to do lateral area first. 1/2 the perimeter of the base times the slant height. Perimeter of the base, there's 6 sides. It's a hexagon. Each one is 6. Last time I checked, 6 times 6 was 36. All in favor, say pi. 1/2 times 36. The slant height in red they gave me was 9. So I get 18 times 9, which is going to be 162 inches squared, which is great, but that's just the 6 triangles surrounding the pyramid. What if I want the base on the bottom? I need that before I can get the whole surface area. So I'm going to use capital B. It's a hexagon, and really, they were nice. They gave you the apothem and they gave you the side length. They only really needed to give you one piece of information, but they gave you 2. Remember, the area of any regular polygon is 1/2 the apothem times the perimeter. The apothem, here's my center, drops to the midpoint of the opposite side is 3 rad 3. And we already computed the perimeter of the base was 36. So if you multiply that, 36 divided by 2 is 18. 18 times 3 is 54. Don't forget the rad 3. So there's your base area. Now you add it on to the lateral area to get the total surface area. Lateral area plus 1 base is area. Be 162 plus 54 rad 3. And we're going to type that in since they asked us to round to the nearest 10th. If you type that in, I'm going to save us some time and not do that on the screen. You can do that on your calculator. That would be 255.5. Inches squared. There's your total surface area. Make sure you read directions if it wants something in exact form or if it wants it to be rounded. Now let's look at one real-world application. I mentioned the Great Pyramids of Egypt. Here's one below, a little aerial view. It says the Great Pyramid at Giza, Egypt was built around 2580 BC, long time ago, as a final resting place for Pharaoh Khufu. At the time it was built, its height was about 481 feet. This is huge. You have to keep in mind this is a real-world object. It's not something you can fit on your kitchen table. This is a massive object. Each edge of the square base was about 756 feet long. Okay. So here's your square base. You're not going to really see the square because it's hidden by all of the sides surrounding the pyramid, all those triangles. They want to know what was the lateral area of the Great Pyramid. Well, the reason we're only finding the lateral area is kind of what I was just saying. If you were going to be a spectator right here going to see the Great Pyramid, you're only going to see the triangular faces when you're standing on the outside in Egypt. That's all you're going to see is one of those 4 faces surrounding. You're not going to see the square. It's going to be inside the pyramid on the bottom. Okay? So we only care about what you can visualize from the outside. That's why we're only finding the lateral area. So let's find that, and let's round it to the nearest square foot, so the nearest whole number. First thing I'm going to do, I'm going to redraw it with my little tripod setup I did before. Connect my square. There's my vertex. I'm going to draw a segment connecting all of those. 1, 2, 3. So there's my pyramid. They told me the base edge, each of the ones on the bottom was 756 feet long. and they told me that the height of the pyramid was 481 feet, not the slant height, the height. So from the vertex to the midpoint of the square, that distance is 481 feet. So I'm going to do my trick. I know I need the slant height in order to compute the lateral area. I'm going to do my trick where I draw my triangle. I'm going to draw the apothem, and then I'm going to connect by drawing slant height in red. So this red piece I'm drawing is the slant height. That apothem that I just drew, I know it's perpendicular to the height since that triangle is standing up on top of the square base. So highlight the triangle we're using. That apothem, like we saw in the 2 problems ago, is going to be half the length of that base edge. Since that base edge is 756, cut that in half. That piece is only going to be 378 if you cut it in half. Okay. And so we need to find the slant height. So here's the right triangle that I'm looking at. 481, 378, and then the piece in red that I labeled was L. We don't need this piece up here. Okay. So, Pythagorean theorem, 481 squared plus 378 squared equals L squared. If you do that, type it in, you're going to get 374,245. Again, real big because this is a real world object. And then we're going to have to remember to square root it since it's being squared. So square root both sides. I'm going to leave it under the radical for now since I'm not done with the problem. And don't worry about breaking the radical down since we're going to be rounding to the nearest square foot at the end anyway. Don't waste your time. Okay, so there's my slant height. So now to get the lateral area, I'm going to do 1/2 the perimeter of the base times the slant height. The base is of length 756 feet for each edge, so multiply it by 4 since it's a square. 1/2 times 756 times 4. Be 3,024. And then I'm going to multiply by, I'm just going to highlight it or underline it, call it star. I'm just going to put it here. So I'm multiplying by that square root that I just found. So let's type that in on my calculator. I'm going to have 1/2, so I'm just going to use 0.5 times the perimeter of the base was 3,024 times the square root of that big number was 374,245. Oh, I lost a digit. There we go. That's what it should look like. Hit enter. Lots of lateral area. You've got 924,975 if I round up, since it's a 5. Okay. So this is approximately, big number, 924,975 square feet. That's how much takes up the triangle surrounding the Great Pyramid in Egypt. Okay. So that'll kind of wrap up our discussion on pyramids. Once we start talking about volume and the inside of 3D shapes, we'll come back to pyramids, but that'll take care of surface area for now. I want to finish up today talking about cones, which are very similar to pyramids, just like cylinders were similar to prisms. Okay. So the surface area of a cone, think of a party hat. Here's a cone. Or your dog might wear it after surgery so that it doesn't itch. The surface area of a cone, it's very similar to a pyramid. Okay, think about how we said a cylinder is very much like a prism. It's got 2 bases. if I was to draw these side by side, you know, there's similarities. There's two bases. Each of them has a height. But the big difference is this one's a prism, this one's a cylinder, because these are circular bases. It has no edges, whereas these guys have edges. Okay? So in the same way, I can compare a pyramid to a cone. They both have one base. They both have a vertex. And they both are going to have a slant height also, and a height. Okay? There's similarities, there's differences. The main difference is, again, there's a circle on the bottom. This is not a polygon. It has no edges, so we can't call it a pyramid. But it's going to behave very much like a pyramid. So the base is a circle, and our favorite constant that always shows up in circles is the number pi. So your answer is always going to involve pi. Sometimes the problem will ask you to leave it in terms of pi, and other times it's going to ask you to round to the nearest tenths place or the nearest hundredths place, so you just need to look at the directions. Different pieces of the cone, very much like the pyramid. You have a height that goes from the vertex of the cone down to the center of the circle on the bottom and forms a right angle. Use letter H for that. That's the altitude. The slant height, I mean, you don't have a triangular face anymore. You just have this curvy part of the party hat. The slant height is the part of the cone that's on a slant. It goes from the vertex, and it hits one of the points of the circle on the bottom. Okay. So you can always make one of these nice right triangles between the height, the slant height, and this is the radius of the circle, since it goes from the center to a point on the circle. You got your radius on the bottom. Okay. And we see the base is a circle, just like we made note of. If you open up the net diagram, if you unfold the party hat, this is what you would see. So this is the net diagram for a cone. To find the lateral area of a cone, we said it behaves very much like a pyramid. So we can use the exact same formula, 1/2 the perimeter of the base times the slant height. But hang on a second. Perimeter of the base is a circle. We call the perimeter of the circle the circumference. So I'm really taking 1/2 the circumference of the circle on the bottom times the slant height of the cone. Well, let's see, can we make that even a little bit easier? What do we know about circumference of a circle? Circumference of a circle is 2 pi r. So if I substitute that in, 1/2 times 2 pi r times L, 2 times 1/2 goes away. That's just 1. And all I'm left with is pi times radius times slant height, pi RL. Okay. Take your pick, whichever one you like. This is one expression you can use for the lateral area of a cone, but this is really what it's going to simplify to due to the fact that the perimeter of the base is just the circumference. So this is the one I always like to use and go to. It's quickest, pi RL. So then the total surface area, this would be like the space of the party hat itself without the part that goes on top of your head. So you got the lateral area, but then you've got the circular base on the bottom that you've also got to compute the area for. That base area is just pi r squared since it's a circle. So LA plus B, which is really just pi RL plus pi r squared. And so let's take a look. Find the surface area of the cone in terms of pi. Means we're not going to be rounding our answer. We're not going to be using the pi button on our calculator. So let's see what they give me. They give me the slanted part of the cone. So that's my cursive letter L for slant height. They give me the distance from the center to a point on the circle. We've seen that from last chapter. That means that this 15 is the radius of the circle on the bottom. So if I want the lateral area first, just the part surrounding the party hat, pi times r times L. And they give me everything I need. Pi times 15 times slant height is 25. I'm going to multiply these two together. 25 times 15 is 375. So I get 375 pi square centimeters. They didn't just say lateral, they want the whole surface area. So I know I'm going to have to add on the base area. Lateral area plus base area. Lateral area we just found was 375 pi. Plus the base area, it's a circle, pi r squared. Radius they gave me was 15. This is the circle on the bottom. So I get 375 pi plus 225 pi. You add that together, you get 600 pi centimeters squared. That's how much surface area you have if you were to paint the outside of that party hat and the circle on the bottom. All right, last page. This one, they don't give you a cone, so we're going to draw the cone. It says the radius of the base of a cone is 22 meters. Its slant height is 10 meters. Find the surface area in terms of pi. I'm going to draw my cone. There's my circle. Meets up at the vertex at the top. They told me the radius, so here's the center of the circle to the edge. That radius is 22 meters. And the slant height, which is along the side, that piece is cursive L, 10 meters. Again, we're going to leave it in terms of pi. So I'm going to do lateral area first, pi times r times L. They give me everything. 22 times pi times 10 be 220 pi meters squared. So that's the surrounding part of the party hat. The part that goes up to the top. Now I need to include the area of the circle on the bottom. So I know the total surface area is going to be that lateral area plus the area of the circle, capital B. So 220 pi, and then I'm going to use pi r squared for the base area. Radius they gave me was 22. So pi times 22 squared, 220 pi plus 484 pi. Both of them have pi's, so I can just add them up as if they were like terms. So I'm going to get 704 pi for the total area. Meter squared. Make sure you put your units on it since units were provided in the original problem. Okay. The next one says find the lateral area and the surface area round to the nearest tenth. If you notice in this problem, they no longer provide you with the lateral area. They give you the height of the cone, and they give you the diameter of the circle. So they're giving you the entire distance across is 26. If the diameter is 26, I'm going to need the radius. Cut it in half. So the radius would be 13 inches. And they give me the height of the cone. Here's H. This forms a right angle. It's perpendicular to the circle on the bottom. I need the slant height. So there's the pink piece that I need. Call it L. Pythagorean theorem comes in again to save the day. These two pieces are radii, so they're each 13. So to get the slant height, first thing I'm going to do, I'm just going to do Pythagorean theorem. 13 squared plus 22 squared equals L squared. You get 169 plus 484 equals L squared. Add those together, you get 653. I'm not going to worry about breaking down that radical since the problem's telling me to round to the nearest tenth at the end. So it would be not worth my time. So just leave it as rad 653 for now. We're going to need that for the lateral area. Pi times r times L. So I get pi times, make sure you're using the 13 and not the 26, since it's the radius here, not the diameter. And then the slant height we just found was the square root of 653. So I get 13 pi rad 653. It asks for us to round stuff to the nearest tenth. I am going to round this here, but then when I go over to compute the actual surface area, I'm going to use this line so that I'm not rounding early to continue my computation. But we will round them individually just because the problem asked us what they are. So I'm going to type in 13. Pi, remember, is second, and then the upside down v, times the square root of 653. Enter, and we get 1043.6. Inches squared. So that's my lateral area. That does not include the circle on the bottom. To get the total surface area, I'm going to take the lateral area and I'm going to add on the circle's base area. So the lateral area, I'm just going to use, I'm going to keep it as 13 pi times the square root of 653. And I'm going to already have that decimal on my calculator. I don't want to round it early on there. Plus the area of the circle, let's just compute that over here. Base area would be pi r squared. So pi times 13 squared would be 169 pi. So on my calculator, go over here. I already have the first part on my screen. All I have to do is hit the plus sign and it brings it down. And now I'm just going to add on the 169 pi. So I get 1,574.6. Use squiggles because we're approximating. And the units in this problem were inches, so we're going to do inches squared. Okay, so that'll do it for that one. All right, last one. Hopefully this doesn't make you too hungry and want ice cream, but this is a waffle cone. Okay. So I said party hats, cones you put on your dog. Ice cream is another great application. What if you wanted to know how much waffle material is needed for the cone shown below? Okay, some ice cream shops have to think about when they're making their materials for ice cream. Okay. They tell me that the opening across the top is 2 inches. So they're kind of trying to tell you what the diameter is. You gotta use a brighter color. So this distance across the top, that diameter, is 2 inches. And the height of the cone from top to bottom, not the slant height, the actual height perpendicular to the circle. So you get 2 different views of it, is 6 inches. That's your height. And I know this distance they gave me before. If the diameter is 2, that means each radius has to be 1 and 1. So I know this is 1 inch for the radius. We've seen this before. We're going to need the slant height. So I'm going to draw it in. I'm going to use that right triangle, Pythagorean theorem. There's L. 6 squared plus 1 squared equals L squared. 36 plus 1 is 37. Notice that's L squared. We need L. I'm going to square root both sides. There's my slant height. How much waffle material? Well, you have to think about the top of the waffle cone is just an open hole so that the ice cream can go on top. This circle that you see is not actually a surface. It's just open. The other day we did an open top box problem. This is an open cone. Okay? I don't care about the circle at the top because there's nothing there. There's no waffle material that I'm using to cover up that surface. So I don't care in this problem about the total surface area. I only care about the lateral area, which is all of the waffle material surrounding the cone, not including the circle at the top. So when it's asking you how much waffle material, aka they're just asking you for the lateral area, not including the circle. So I just need pi RL. Pi times the radius was not 2, it was 1. We cut it in half. And then the slant height was rad 37. Pi times 1 is pi. So on my calculator, I am going to round this one because I'm not going to be asking somebody, hey, how much waffle material did you use to make that ice cream cone? Oh, I used about pi times the square root of 37 inches squared. Your friend's going to look at you and say, huh? Nobody talks like that. So we're going to type it in and redeem ourselves. Pi times the square root of 37 is 19.1. So we're just going to round it to the nearest tenths place. 19.1 inches squared. That's how much material you would need to make that waffle cone. And then you go eat your ice cream. Pick your favorite flavor. I like cookies and cream and mint chocolate chip, but I know it's not for everybody. That's it. All right, so that'll do it for pyramids and cones for now until we get to the concept of volume. There will be an assignment posted for Math Excel, and there will also be a practice worksheet for this section as well. Happy mathing.